Welcome to the 10th chapter on differential equations and differential invariants in the Logical Foundations of Cyber-Physical Systems textbook. We have graduated from our study of elementary cyber-physical systems, which calls for celebration. But we're now leaving the realm of cyber-physical systems whose differential equations are solvable in closed form, which is a significant departure and substantial generalization from elementary CPSs to advanced CPSs. And if we worry about CPSs whose differential equations do not have closed form solutions, then the cyber-physical systems become significantly more challenging, but also significantly more interesting. And this change is just as noticeable and significant as the change was from single-shot control systems that control once or twice to systems with an unbounded number of interactions in a control loop. All of a sudden, we can no longer pretend that each ODE could actually be replaced by an explicit representation of a solution that describes as a function of time the state that the system is going to be at, so that with the quantifier overall times, we can capture all the behavior that the differential equation could have. Instead, what we're going to do is develop the logical groundwork for analysis techniques of differential equations that understand them implicitly based on the actual dynamics as opposed to replacing them with a solution. And that marks a remarkable shift in perspective, opening up a new world of fascination in the continuous dynamic aspects of CPSs. And how it starts is by giving entirely new meaning to the primes in CPS models. Why do we want that? Well, because our limited understanding of differential equations so far was following the mathematical reflex of given an ODE, you just right away begin to solve it, which is amazing if you can solve the ODE. But remember, ODEs were easier than their solutions. That means we would possibly make our analysis of them unnecessarily complicated if we first insist on solving them. What we will be developing now are rigorous reasoning techniques for much more sophisticated differential equations that will ultimately actually make the reasoning principle of understanding ODEs via their solutions completely irrelevant and superfluous. Granted, you may have seen a whole range of different methods for solving differential equations, which are very helpful for many common cases. But in a certain, even technically precise sense, most differential equations are actually impossible to solve because they don't have any explicit closed form solution with elementary functions. Which is why we will be reinvestigating differential equations now from a much more fundamental perspective, by seeking unexpected analogies among what looks like completely different phenomena, namely the discrete dynamics and the continuous dynamics of systems, which it turns out actually have a lot more in common than you would first suspect. Discrete systems, well, they're very complicated indeed, but they do have a powerful ally, induction, as a principle for establishing truth for properties of discrete dynamical systems by generically analyzing the one step, the loop body that it executes repeatedly. That's what induction ultimately does. What if we could do the exact same induction principle for differential equations in order to understand them without first having to have written down a complete global solution and then inspecting whether that particular solution satisfies the property at every time? What this requires us to do is understand what the generic local step is that a continuous dynamical system performs repeatedly as it is being followed. But of course, the tricky bit is that continuous dynamical systems, the one thing they're not so good at is doing steps, because one step at a time is the kind of thing that discrete dynamical systems do. So that's where this fundamental subtlety lies. Overall, this chapter is of absolutely central significance for the foundations of cyber-physical systems. It plays just as pivotal of a role as our 5th chapter on dynamical systems and dynamical axioms played for the rest of CPSs. But we're really getting ahead of ourselves. So let's get started with what we're going to learn in this chapter. From a modeling perspective, we will develop a deeper understanding of the continuous dynamics that is, without any doubt, fundamental to CPSs. We'll also learn how discrete and continuous dynamical systems, even though they come from fundamentally different sources, actually relate to one another a lot more closely than you might think. In fact, on the long run, this turns out to open up very interesting similarities between the two. On the computational thinking side, we're looking at, well, analogies of discrete versus continuous systems, and we will be exploiting them to develop rigorous reasoning techniques for differential equations, which are, of course, completely fundamental. Why? Because without rigor, it is often impossible to understand the intricate behavior and spot any subtle issues that you might have in your control, or say for sure whether and why a design is no longer faulty after you've fixed it. Rigor is necessary for the subtleties that CPSs have in store for us. And since CPSs do include differential equations, we better also have rigorous reasoning techniques for those differential equations, and that shouldn't stop with worrying about their solutions alone. Which is why we will be looking at induction principles for differential equations, which will lead us down a path of axiomatizing differential Deming logic, and will enable us to study basically the differential facet of the logical trinity, that is studying the relationships of syntax, semantics, and axiomatics. On the CPS skills side, we will develop a deeper understanding of the actual semantics of continuous dynamical aspects, even though we've done just fine so far with it. And that will lead also to a better intuition for the operational effects that continuous dynamical systems have on CPSs. The entire chapter is overall, in addition to exhibiting semantic nuances of continuous dynamical systems, absolutely fundamentally critical to rigorous reasoning for all but the most elementary cyber-physical systems. Remember the logical trinity, whereby we're studying syntax, semantics, and axiomatics, where the syntax just defines the notation, what kinds of problems are we allowed to write down, but the syntax was quite arbitrary. The semantics is what carries the actual meaning, so what real or mathematical objects does the syntax stand for? And the axiomatics internalizes semantic relations into universal syntactic transformations. For example, ask yourself, how does the semantics of E equal E tilde relate to the semantics of E minus E tilde equals 0? Syntactically, they of course should have the same truth value. So you should enable syntactic transformation from one to the other back and forth. But now what happens if derivatives enter the mix? Say in the middle of a differential equation whose properties you're interested in. Which means what we will be developing is the differential facet of this logical trinity. Let's begin a gradual introduction into the principles of differential invariants. Remember these differential equations that we looked at in the 2nd chapter? And here's their solutions. Don't even look at them individually, but you'll notice that pretty simple differential equations, constants have linear functions as solutions, linear functions have exponentials, for example, as solutions. There's sine and cosine functions coming from pretty simple linear differential equation systems. And the point is that the solutions are much more complicated than the differential equations themselves. But that's part of the descriptive power of differential equations. The entire point is that differential equations characterize the continuous evolution of physical processes or other processes only locally by the respective direction into which the system goes. And it's much easier to say, even if the global behavior is very complicated, to say, well, locally it's going this way. Even very complicated physical processes are thus described by fairly simple differential equations, which means there's a gigantic complexity difference between the local description, which is simple, and the global behavior, which is complicated. But now, that explains why differential equations describe complicated processes in very simple ways. But if for analyzing differential equations, we work via their solutions, follow the mathematical reflex of solving every ODE that anybody ever gives you, and then look at the solution, that has the problem that it undoes their descriptive power. So what we will be doing is exploit the difference in descriptive power of differential equations compared to their solutions, also for analysis purposes. Which means we should be doing proofs about the differential equations themselves, as opposed to indirectly proofs about them by first worrying about their solutions. For example, this differential equation, second time derivative of position is minus position, that has as a solution the sine function, which is not only much more complicated, but in particular it is not part of first order real arithmetic. Why? Well, because it needs infinitely many powers to be written down precisely, and writing anything down infinitely is kind of awkward because you'll never be done with it in finite time. Of course, you can write down the sine function, but then you still need to explain what the sine function really is. Moreover, actually, could Gödel indirectly prove that arithmetic with sine functions and cosine functions and so on is undecidable, because they do contain copies of natural numbers. Moreover, this differential equation, x double prime of time, is e power t squared. Well, I mean, it's a complicated one, but the point is, it doesn't even have an elementary closed form solution at all, so we cannot possibly work with it by first even writing down the solution. Instead, let's work with the differential equations themselves. You also prefer to do loop induction instead of unfolding all the loop iterations globally, of course. If somebody gives you a loop, you wouldn't first write down all the behavior that it has for eternity by unfolding it one loop iteration at a time and then worrying about that. And if we work with differential equations by way of their solutions, we're doing essentially that. We first unfold the differential equation into their global behavior, which is very complicated. If we're done with that and we still find a concise closed form solution for that, we can then worry about the description of this. But wouldn't it be much more interesting to prove properties of differential equations locally from their dynamics? So let's develop this. Induction works beautifully for loops. If you imagine this differential equation would be a loop, then how you prove inductive properties about it is to prove that some induction property f is true in the beginning, that if f is true now, it's true again after one round of a loop body, and if it's true at the end, then it doesn't imply the post condition you want. If only we could make something like this induction principle work for differential equations. It's fairly easy to see what it means to prove that it's true in the beginning and to prove that if it's true at the end, it does imply the post condition. But of course, the culprit is the question, what is the counterpart of the induction step? What does it even mean in a differential equation to say, well, if it's true right now, then it's true next time around? Because differential equations have no next time, because time is a continuously varying quantity. You know, the time right after 1.57 seconds is not clear. Now, contrast this with what we've done with solutions of differential equations. Of course, we can say a property is always true after a differential equation if assuming we happen to be given a solution of a differential equation, actually a solution of the symbolic initial value problem that starts off the differential equation at the initial value about which we don't know anything except that we can call it x. And if we have generic solutions for this, then we can replace the question whether the property p is always true after an ODE by the question whether for all times t, if we insert the time t into the solution y, and then change the value of the variable x to be y of t by a discrete jump, if then p is true under all of those circumstances, then that's exactly the same as to say that p is true always after the differential equation. But what that does intuitively is, if here we're plotting the right-hand side of a differential equation, so at every point of the, in this case, two-dimensional state space with x1 and x2 variables, at every state are we plotting in which direction the system evolves, then this would correspond to one of those global solutions, right? A solution that starts here and always follows the right-hand side of a differential equation, which is plotted as vectors here. But of course, we can't even know what this particular initial value is here, x, because we're supposed to solve it for each and every one of those points. So for example, we're also supposed to solve it here, which will go that way. Now, if we ask ourselves, do we ever get into the bad blue region, we can in principle, start the solving everywhere, computing solutions everywhere, and check at every point in time whether we enter this bad blue region. And the only reason this actually still worked well is because we didn't do it literally in this axiom. What we did in this axiom was work with symbolic initial value, where we say if we have a representation that describes for every point what the behavior is over time, and if that fits into the real arithmetic, then the real arithmetic quantifier for all times in front of it precisely says that at every point in time are we in the bad blue region or not. But it does depend on us finding a solution that is in real arithmetic, and the quantifier around it is what Tarski's quantitative elimination miracle can handle for us. Of course, it's somewhat short-sighted. But the point is, it's not like we really need to know what the solution is in order to be able to tell whether it's inside the bad blue region or not. Instead, what we want in an induction principle is to say here that the formula f remains true in the direction of the dynamic. So if it was starting out somewhere true, and we follow the dynamics, then it's always going from a state where it is true to a state where it is true again. Of course, the going from a state to a new next state is kind of sort of undefined in differential equations, so we have to be a lot more careful about that. But the advantage is, at least we don't need to know where exactly the system evolves to, right? We just need to know that it doesn't go somewhere unsafe. So intuitively, if we start here and the system pushes us into an unsafe direction, if it were to do that, then our system could possibly follow that and make us unsafe. But if this never happens, then intuitively, if we start somewhere safe and all the vectors point us from safe to safe and from safe to safe and from safe to safe and from safe to safe, then even if we don't know where exactly we end up, we still know intuitively it must have been somewhere safe. So we need logic that enables us to speak about the direction into which a formula is evolving along a differential equation, and have a way of justifying that that remains true. Let's look at a guiding example to figure this out. Here's a simple example that is saying if v squared plus w squared is r squared, then always when we're following this differential equation, v prime equals w and w prime equals minus v, it remains the case that v squared plus w squared is r squared. Please resist your urge and temptation to solve this ODE. Don't even worry about it. Here is the solution. Okay. It is following basically a rotation in the circle. So one of the coordinate variables will be a sine function, for example, and the other one will be a cosine function, or it could be mixes of the two. And yes, sine squared plus cosine squared is 1, but we're not supposed to worry about solutions. How can we establish that v squared plus w squared is r squared all the time without first worrying what the solution is? Let's just write it down and see what we get. We can, of course, apply the proof rule that says that should be the same as v squared plus w squared minus r squared equals 0. And from that assumption, we prove that v prime equals w while w prime equals minus v. Following that, it is always the case that v square plus w square minus r square is 0. That's just using the implies left proof rule. Okay, what else could we be doing? Well, if we're not supposed to solve the ODE, I guess we can worry about how the post-condition expression changes. Ooh, it's true in the beginning, that's a good thing. How does it change? Well, I guess it changes by some sort of derivatives. So I guess it changes in 2 times v, and the next one changes as 2 times w. And I guess r shouldn't be changing, so I guess the remaining thing is just equal 0. Because r is a constant. But that's not actually right, because of course how v squared changes, if we form the derivative, is 2 times v, but it should also depend on how v itself is changing. So why don't I say v prime for that? And likewise over here, the derivative of w squared is sure 2w, but it also depends on how w itself is changing. Why don't I just call it w prime? Okay, how do I prove that? I guess I forgot, but it does make sense to write in. What's more natural than writing in w for v prime and minus v for w prime? Let's just do precisely that. 2v times w plus 2w times minus v. That's what we're supposed to show is 0, and oh good, it is. I mean, these two cancel, so the whole thing is 0 equals 0, and that's just another way of saying the whole thing is actually true by real arithmetic. And the only question is, of course, what particular proof rules have I been using here? And are they actually proof rules? And the first question that you will ask after logic training that we've now got is, yeah, sure, nice, but what does he mean by v prime here? Let's develop this one step at a time. Let's augment differential aiming logic with differentials, so a first-class citizen representation of primes in the language. Well, this was our syntax. A term can be a variable or a constant such as 77, or a sum of 2 terms, e plus k, or even a difference of 2 terms, even though we indirectly represented it, a multiplication of 2 terms, or maybe sometimes even division of 2 terms. But since that is our syntax, I mean, we should be able to maybe say that we know how to form their derivatives. Well, because what is the derivative of e plus k? Right? I guess it should be the derivative of e plus the derivative of k. What should be the derivative of e minus k? It should be the derivative of e minus the derivative of k. What is the derivative of e times k? Well, it's the derivative of e times k plus e times the derivative of k. What's the derivative of e divided by k? Well, that should be the derivative of e times k minus e times the derivative of k divided by k squared. What's the derivative of a constant? Well, I guess that's 0. That makes a whole lot of sense in principle, but of course we'll have to worry about what we mean by derivative. Is this a time derivative? Time derivative of an expression? Here we should be worrying about dividing by 0. Could this actually be undefined? What do the primes mean to begin with? Well, let's take this one step at a time. Let's actually syntactically internalize the concept of primes into the differential aiming logic syntax by officially admitting into the term language also the primed version of any term. Say, whenever e is a term, e prime also is a term. Okay, that's good. Now we can officially syntactically write it down, because previously we were not allowed to, so everything I wrote down here wasn't actually quite really okay. Wasn't in the syntax, at least. That leads us to this next question. What's the prime supposed to mean? What is the meaning of a prime? Well, in logic, at least we know exactly how to begin with such a question. We know exactly that the meaning of a term is a function that maps states to real numbers. Wonderful. So what we need to define is the meaning in the state omega of the new term we just added, e prime. Good, so we know where to begin. What then is the meaning of the term e prime in the state omega? Well, surely that's the time derivative. It's the derivative by time of the value that the term e has in the state omega. Wonderful. No, wait, not wonderful. What's the time derivative? What's time? I ask myself, what's the time every morning? But I mean that here in a much more fundamental way. What does it mean to derive this expression by time? There is no time in the question what the value of the term e is in a single state omega. Maybe it depends on the differential equation. We should say, well, okay, what the time derivative is a function of the differential equation that we're actually currently worried about. So remember, the vector field of a differential equation looks like this. So for every point in space, the differential equation says in which direction the system evolves. Should we say the meaning of e prime in a state depends on what differential equation we've been talking about? That shouldn't be the case either, because the meaning of nothing should be depending on the context in which you need it. Right? The meaning should be a compositional function. Right? The meaning of every syntactic object should be absolutely the same meaning every time you use it, no matter what context you're using it in, no matter what purpose you're using it for. If you ever break this principle, you're in deep trouble of understanding every part of it. The meaning of 5 shouldn't depend on where I use the 5, right? The meaning of a variable x shouldn't depend on where I use it, although maybe possibly its value could be changing because I'm referring to it in different states. But it's still always the state I ask to find out what the value of the meaning of x is. So that isn't working very well, I guess. The real fundamental observation is that we've been asking ourselves what the meaning of a derivative for e prime is in a state omega, but in a single isolated state, there just are no time derivatives to speak of. It's not mathematically meaningful. You need at least an open set around you to define any derivatives at all. Of course, no time derivatives exist without time. That's the whole point. Why do I emphasize this? Because it's so easy to mislead yourself into believing in verification approaches for hybrid systems that make subtle mistakes that are exactly analogous to assuming derivatives exist in isolated states. Let's try not to do that. Let's try to do it regardless. We're trying to give meaning to e primes in a single state, and I guess that's complicated, but we can still say at each and every one of those states, e prime has a meaning as a function of the meaning of the derivatives. So as a function of what the value of x prime is, you can give a meaning to e prime. In other words, it is a differential form. It's a mapping that maps to a real number, every state of a state space together with the state that the derivatives have at that moment. So for example, it would be different at this state, but also it would be different depending on whether you have the blue direction, or you follow the red direction, or you follow the direction that's already there. In other words, what we're defining is the meaning of the e prime terms in a state omega is the sum over all variables of the value that the x prime variable has in the state multiplied by the partial derivative that the value of e has in the state omega as you're varying the value of x. Remember, what are partial derivatives? The partial derivative of the value of e in the state omega as x is changing is the limit as a variable kappa is approaching the value that the variable x has at state omega. So we're getting closer and closer and closer to the value that x has at omega, of the value of e in a state that looks like omega, except it has the value of the variable x replaced by kappa instead, minus the value that in the original old state omega e does have, divided by, well, how close is the kappa to the value omega of x that the kappa is converging to. And then this limit is what a partial derivative is. Just how does the value of e change as you're changing x in the current state, multiplied with the value that the x prime variable has, which is reflecting intuitively at the moment in the state we're currently talking about. Remember this picture, what direction is x evolving into. That means the meaning of these differential terms, e prime, is exactly a differential form, something that gives us the value as a function of the how the expression e depends on the values of the variables x, everyone that's in it, multiplied how do the values themselves change? So how does x prime, what value does x prime have at the moment? Which is a local question, so that we can make local sense of if we simply enrich our states to have values for all the variables and all the primed variables. But hey, that really just means we should call a prime variable x prime yet another variable. That's precisely how we're meaning it. Remember, we've actually already done that when understanding the semantics of differential equations, because the semantics of following a differential equation within an evolution domain constraint is a reachability relation, remember, that takes us from the old state that we had at the initial point to the new state we have at a later point in time r, for some r that is greater or equal 0, such that we do respect the differential equation at every point in time z along this solution, which just means we're making the formula x prime equals f of x and q, true, the q that comes from the evolution domain constraint, for a solution of any duration r, but the x prime needed a value and the meaning, of course, in order to be able to ask whether in the state phi of z is the logical formula x prime equals f of x and q true. And for that, we used to say already in the second lecture, in the third lecture, that the value at time z of the variable x prime, had it already there, is the time derivative that the value of the variable x at over time t, as the time is changing, has at the intermediate point in time z. Notice a slight subtlety. What we also are doing here is actually saying that it's a solution from the initial point in time 0 to the new time r. Everywhere except this. What does that mean? On the complement of the set x prime. That means everywhere except for the value of x prime. Let's zoom into that. So that's supposed to be a relation that goes from the old state omega to the new state nu, as you see in this picture, old state omega to the new state nu, such that the old state should be equal to the value that the solution has at time 0, and the new state should be equal to the value that the solution has at time r. But we mean that actually only except for the initial value of x prime. So the notation that you've seen here with the except at x prime at the beginning is exactly meaning that the initial state is identical to the initial data that the solution has except for the value of x prime. Why is that important? Well, because the value of x prime is supposed to be this time derivative right away. I mean, there's no reason to believe it already starts with this time derivative. In other words, what we have already done is that along a differential equation, x primes have very well-defined meanings, namely they exactly correspond to the time derivatives that the values of x have over time, but at most moments time derivatives are actually even meaningful. And we also said that the initial value of x prime is irrelevant because now we're supposed to follow x prime equals f of x even if x prime wasn't f of x yet in the initial state, but also the state that comes out of it at the end, right, still carries the last value of x prime forward into the future in case we need to repeat it. All of this setup was actually very important. In every isolated state, if the state carries a value for the x prime variable, we can certainly refer back to it and use it in our evaluation of terms, but only in the middle of a differential equation, such as here at this point in time, can we meaningfully identify the value that the x prime variable have with the time derivative over time, because at least along a differential equation solution, there is a well-defined notion of time. You can do that while you're following a differential equation to say, I guess x prime is the same as the time derivative, but you cannot do that in the rest of the evolution of your hybrid system. Why? Well, because there can be discrete switches, there can be even discontinuities, and if you have a discontinuous function, say you're jumping at the end and following something else, then there is no time derivative to speak of. Only while you're in the middle of a differential equation can you get to assume that x prime has a time derivative value. If you're anywhere else in the state of a system, you cannot possibly assume that. Now, this, however, enables us to identify a very fundamental link between the two. Yes, E prime, the differential term belonging to E, is just a syntactic expression. This syntactic term, E prime, we can evaluate in a state, but if the state we're evaluating it at happens to be a state along a solution of a differential equation, so if phi is a solution of a differential equation x prime equals f of x, and also satisfying an evolution domain constraint Q, so it comes out of one of those solutions of the hybrid program's continuous differential equation system, then at least if we've been evolving for actually a positive amount of time, then for every intermediate point in time, as long as the free variables of the term are at most the ones that the differential equation is talking about, it is true that the value at time z along this solution phi of the purely syntactic expression E prime is equal to the time derivative, which is defined because the solution is of a positive duration, is equal to the time derivative at the same time z of the value that the original term E has at the time phi of t as the time t is changing. And that means a purely syntactic expression, E prime, it's just a syntactic term that we have right on the left-hand side, is in value equal to the analytic time derivative that we have of the original term E. In other words, syntactically we've added primes as differentials into the logic, but the meaning of this syntactic expression happens to coincide with the meaning of the analytic time derivatives we have, as long as those time derivatives are even meaningful. That means while we're following a differential equation, syntactic values happen to coincide with analytic derivatives. But remember, the value of E prime was actually this differential form expression. Also, what we read off from it is that while we are following a differential equation, meaning if phi is a solution of x prime equals f of x and q, well, then we at least know that I guess x prime has the value that f of x has. That's what it means to follow a differential equation. And that means always along the solution of differential equation, it is also true that p is equivalent to p after assigning f of x into x prime. Well, why? Well, because as we're following the differential equation, x prime equals f of x prime already always has the value that f of x has. So if we assign it into this again, it's like nothing actually happens. This is a way of logically exposing the effect that differential equations have on the x prime variable, namely to make them exactly equal to f of x at every moment. And all of a sudden, we can also meaningfully ask, in addition to having understood the effect on differentials, in addition to having written in the differential lemma the relationship between the differential value and actual analytic time derivatives, we can also make sense of what these were. All of a sudden, these are just equations of differentials. This is a differential, it's just a syntactic expression that happens to mention a prime. This is another syntactic expression, one that has pluses and mentions primes, but both of them are individually very meaningful because primes in terms are ordinary syntactic operators and have a meaning in every state. And that means all of a sudden also this equations has a meaning. It could very well be that the value of the differential of e plus k happens to equal to the value of the differential of e plus the value of the differential k. And indeed that is the case. Likewise, the differential of e times k is equal to the differential of e multiplied k plus e times the differential of k. The value of the left-hand side is really always equal to the value of the right-hand side, which means this equation is a valid equation. For example, we will be adopting it as an axiom. And it is also true that the value of the differential of a constant is 0, because remember what the meaning of differential said? It was, sum up all the partial derivatives times the co-state x prime values. And if we take the value of c and modify the value of all kinds of variables, the partial derivatives will be 0 because variables don't occur in the constant. Take the derivative of 7, it's 0. Take the derivative of a constant for pi, it's 0. And also, we can learn that the differential of a variable x is the same as the x prime variable. So notice we're writing differentials always with parentheses. So on the left-hand side, you have a differential of a term that happens to consist of a single variable, but it's a differential. On this side, we've written down the prime variable, x prime. And yes, fortunately, the equation is true that the value of a differential of a variable is equal to the value of its prime symbol. But none of them are crazy fancy concepts. All of them are just equations of differentials. And in fact, it will turn out that our study of differential equations will lead us to studying equations of differentials instead. Let's understand what we can do to capture the differential assignment lemma, which is a semantic principle, and make it accessible as an axiomatic reasoning principle in our logic. Well, since along a solution of a differential equation x prime equals f of x and q, it is always the case that a formula p is true if and only if p is true after assigning the value of the right-hand side f of x into the prime variable x prime. Since that is the case, it's also the case that the differential effect axiom is true, which says that always after following a differential equation x prime equals f of x within an evolution domain constraint q, is the logical formula p true, if and only if always after following the exact same differential equation is the formula p true after we put the value of the right-hand side f of x into the primed variable x prime. Precisely capturing this, right? After this differential equation, we apparently always are following one of those solutions, and after that differential equation, the formula p is equivalent to what happens if we assign the value of the right-hand side of the ODE into the left-hand side of the ODE, which is precisely what we're doing here. Wait, why do we have to do that? If it's always equivalent, doesn't that mean it's already clear that these are equivalent? Well, yes, of course it is, but we also need to make that knowledge accessible syntactically in the logic. So here we have a formula p as a postcondition of a differential equation, and the axiom tells us that we can copy the discrete shadow of the differential equation, the effect that it has on the prime variables. We can copy that into the postcondition if we need it. And the two are equivalent because, well, that's precisely what the differential assignment lemma says. Also, we will be able to read off from that the differential induction principle. What's that? This thing. It says that since the value of the differential of E along a differential equation, otherwise who knows, is equal to the value of a time derivative of E, we can conclude that if we know, this is backwards implication, it's just the same as this implies that, just written in a backward style to make it easier to identify what we're really interested in, which is always the blue part of the axiom. So, if we know that always after following a differential equation x prime equals f of x, e prime is 0, then we know that this left-hand side, the value of the e prime term is always 0. But since along this differential equation the value of the e prime symbol is equal to the value of the time derivative, we also know that the value of the time derivative of e is always 0. If we know that the value of the time derivative of e is always 0, we of course know that e isn't changing. And that means we know that always after the differential equation x prime equals f of x, same as over here, we know that e is equal 0 at all times if and only if e is 0 right now. Sure. This means the value of the differential is always 0 after the ODE. That means by this the value of the time derivative is always 0. That means it's 0 all the time if and only if it's 0 right now. Where you should read intuitively in this axiom the differential of e, the e prime, as the rate of change of e along the differential equation. And if that's 0, it's 0 all the time, if and only if it started at 0. Let's take these reasoning principles and add them all together in order to justify why we didn't actually make a mistake in the intuitive proof we scribbled down. Using the differential invariant proof rule. The one that says if e is 0 in the beginning, then e is 0 all the time after following the differential equation x prime equals f of x. In order to prove that, it suffices to prove that if I assign the right-hand side of the differential equation f of x to the left-hand side of the differential equation x prime, notice this is an assignment, whereas this is a differential equation we're following for a continuous time, that's a discrete time operation, then if we prove that the value of the differential of e prime is 0, if we prove this induction step up here, we have proved that e equals 0 remains true always along the differential equation, if only it was true in the beginning. How we justify that is by combining the differential invariant axiom with the differential effect axiom. Remember, the differential invariant axiom said that if I know that the differential of e prime is 0 always after an ODE, then after an ODE in equation e equals 0 is true all the time, if and only if it's true right now. I do know that it's true right now, so I guess I would also be able to conclude that it's true at all times, if only I would know this. That, however, is a different question than this, no matter how syntactically close they are. This is the question of always after a differential equation something, something, something holds true. These are the kinds of things we're trying to prove. So this had better be an easier question than that, and yeah, it is, because something got easier. We've got the differential right here. We still need to get rid of the differential equation. But also, before we get rid of the differential equation, we need to carve out what the effect of the differential equation is on the prime variables. Remember, e prime will ultimately be a function of what the values of its variable primes are. Semantics is e prime, y prime, and so on. Semantics, we better identify that. We do because we use the differential effect axiom here that says x prime can be assigned to f of x after a differential equation because the property, any property p is true always after it, if and only if it's true without that. And that means from the differential invariant axiom and the differential effect axiom, the differential invariant proof rule, little di, can be derived as follows. We're proving that by the differential invariant axiom, this follows from that, as is written here, if only we have a proof of that, written down here. Now we use the differential effect axiom to say some question is true after an ODE if and only if it's true by first copying the discrete assignment version of the differential equation out. Done that here. Then we use Gödel's generalization proof rule to say one way of proving a property of a differential equation, and in fact, one way of proving a property of any box of a hybrid program is to just prove the darn post condition. We're doing that now by the Gödel's generalization proof rule. Remember what we did with loops? We had the loop iteration axiom, which reduced one property of a loop to another simpler property of a loop. We ultimately elided the loop by way of the Gödel generalization proof rule. And we're kind of sort of doing that again here, right? Even though we keep the differential equation for some time, ultimately it goes away by the Gödel generalization proof rule. And now, all we have is this as a sub-question, and that's precisely what we conjectured up here. That means the differential invariant proof rule really is a derived proof rule. It follows completely directly from the differential invariant axiom and the differential effect axiom just by combining them together with the familiar Gödel generalization proof rule. That's good, because now, when we're using this proof rule, it reduces a question about a differential equation to a significantly easier one, a one that's just about assignments. And hey, assignments we know how to handle by substituting them in. Let's practice this in our guiding example and see whether we've actually developed the principles in a correct way that we need in order to make sense of our intuitive arguments. Because only if we can make sense of them with sound proof rules only or sound axioms only are they actually correct to be used in rigorous reasoning. So here it is. We have an implication on the right-hand side that is pushing the assumption on the stack of assumptions, and it asks us to prove the right-hand side of a differential equation. Now, by the differential invariant proof rule that we just developed on the previous slide, does this turn into the question that we leave the discrete shadow of the differential equation around? So we assign the right-hand side of a differential equation to the left-hand side. So we assign w to the variable v prime, and we assign minus v to the variable w prime, and ask the derivative of the post condition. Wait, there wasn't a derivative really. It was a differential. So we did form the differential of v squared plus w squared minus r squared, and we used the equations for differentials to say, well, but the differential of v squared, that's just the differential of v times v, and that is, do it yourself, in an exercise, 2v times v prime plus 2w times w prime minus 2r times r prime. What's with r prime? Well, r doesn't have a differential equation, so I guess r prime should be 0. So okay, let's put 0 in for r prime because hey, it hasn't changed, right? And then here we use the assignment axiom, which just for clarity I write with an extra prime in it here, since we're doing an assignment for a variable that happens to have a prime, but it's not that important that I do. Replace the left-hand side of the assignment and the left-hand side of that assignment also with the right-hand side of the assignment. So wherever there was a v prime, we write w. Wherever there was a w prime, we write minus v. But that's now a very harmless operation, right? The hard one was to justify whether this differential invariant proof rule is sound, which just follows from the differential invariant axiom and the differential effect axiom. And now we have 2vw plus 2w minus v, which overall, of course, cancels and gives us a very simple real arithmetic proof, which enabled us to do a proof of this property without ever solving the differential equation, just by differentiating the question. Prime, 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 prime everywhere. And that's super exciting. Let's do that again on another example. Here's the question where we ask if we start where this is true, is this really always true after we're following a differential equation? X prime equals minus x squared, while y prime is 2xy. Let's push the assumption on the assumption stack with the implies right proof rule. And again, we prove that by differential invariance because I don't want to solve this thing. And so we take the differential of the post condition, which is the differential of x squared y is 2x prime times the right-hand side plus the left-hand side x squared times the right-hand side derived, so y prime, and the differential of the constant is 0, and that just stays 0. and we copy the discrete shadow of the differential equation. So we have the x prime is assigned to be minus x squared, while the y prime is assigned to be 2xy. Now we do something harmless again. Now we use the assignment axiom to put in minus x squared for x prime, and we put in 2xy for y prime. Let's do this exactly that. Here we've got then 2x minus x squared y plus x squared 2xy. And let's see, that cancels because this gives us minus 2x cubed y, and this gives us x cubed y multiplied with 2. So we have a proof. Yes, indeed, if this property is true in the beginning, then it's true all the time when we're following the differential equation. For example, here. In fact, other invariants are also provable in very similar ways from this dynamics. Differential invariants, as we've just seen, are a very powerful reasoning principle. But we had better make sure that they're also really sound themselves. Otherwise, they would get us into a lot of trouble. This is the slide with the lemmas that our arguments were based on. The differential lemma says that the e prime, which is just a syntactic term, is the differential of a term. The value of the syntactic expression is equal to the value of the analytic time derivatives, at least as long as we're following a differential equation for a positive duration. That at every moment in time, is it true that the value of the differential e prime of e at the time z along the solution equals the time derivative along that solution that the value of e itself has at the time z. This is an analytic derivative, this is purely syntactic. We better prove it. The differential assignment lemma, we should also be proving. It's more obvious though, because x prime equals f of x was exactly one of the effects that the differential equations had, so it deserves a proof, but it's easier to see why the formula p is equivalent to the formula p being true after I assign f of x to x prime. And we also need to prove the soundness of the equations of differentials that we've used. For example, that e plus k prime is e prime plus k prime, and the Leibniz rule that e times k prime is e prime times k plus e times k prime, and so on. So let's justify the soundness of these. The proof of the derivation lemma for the equations of differentials I will leave for next time. Let's quickly do the correctness proof for the differential assignment lemma. Property is true if and only if it's true after assigning the left-hand side of the differential equation to become the right-hand side of a differential equation while we're following a differential equation. That is exactly part of the effect that differential equations have, namely that while we're following a differential equation, that really means at all times is x prime equal f of x and q true, where, of course, if x prime equals f of x is true along a differential equation, that precisely means it doesn't matter whether I assign x prime to have the value f of x again along this differential equation, because it already does. So this is like a no-op. It's an important no-op, remember, because we use it in the differential effects axiom to make it accessible in our syntactic reasoning. But its correctness is obvious. The more subtle part is to justify the correctness for the differential lemma. Let's do that. What it is saying is that the value of a syntactic object, the value of the differential of e, the e prime term, is equal to the value of the time derivative of the value of e itself as time is changing at time z that we're talking about, at least along a differential equation of a positive duration. Otherwise, if it doesn't have a positive duration, there's no good time derivatives to be talking about. We got that problem already. Let's not do that again. So here we're copying down this right-hand side on the left-hand side just to confuse you. Then we have the value of the evaluation of the expression e at the time t of the solution, which by chain rule is exactly the sum over all variables of the partial derivative of the value of e bar every variable you could possibly think of at the time phi of z, multiply it with the time derivative of how phi itself changes, so how phi of t changes at the value of the variable x that we're doing the partial derivatives over at the time z. Chain rule, right? It's derive the partials of the outer functions at the inner time, multiply it with the derivatives of the inner function at the same time. Now, for this, we know an expression, namely precisely along a differential equation, this is equal to the value that the x prime has at time z. So that is precisely equal to keeping the left-hand part exactly as is, but replacing this with the value that the x prime variable has at time z. And now we relate this to the semantics of this, which we've recalled here. The value in a state omega of a differential term, e prime, is the sum over all partial derivatives by all the variables x at the state, multiplied with the values of the co-state, the x prime variables. Now, remember what we want here is a state omega that is a state along a solution of differential equation. Let's plug that in. In that case, it means the semantics of a state at time z of a solution of differential equation of a arbitrary differential term e prime is the sum over all, partial derivatives of the value of e at the state, which now has a different name. It's now the state that happens to be the state at time z that the solution has, multiply with still the state at time z that the solution has, but now of the co-state the x prime variables. And then we notice, of course, that this and that, they're actually equal. We just flip the order of the multiplication here. So here's a multiplication, and there's a multiplication, and we flip them. And that, of course, means that indeed, following the equations, that was an equation, following the equation this way, we end up finding the left-hand side out of having started with an equation from the right-hand side. So yes, we do have a proof of the differential lemma. Where do we use the assumption that the duration is positive? Well, because otherwise there is no time derivative, so it isn't even well defined. And of course the chain rule doesn't hold if there is no time derivative, because it's talking about time derivatives. So let's summarize what we've learned today. What we've seen is the differential invariant proof rule, at least for the case of equations of zero. That we will generalize next time, but it's still an extremely useful starting point. And this differential invariant proof rule says that if we know that e equals 0 in the beginning, and then we know that e equals 0 all the time after the differential equation x prime equals f of x, for proving that, it suffices to prove that after assigning the right-hand side of a differential equation to the left-hand side of a differential equation, the differential e prime of e is equal 0. This differential invariant proof rule derives directly from the more fundamental differential invariant axiom that says that if we have a proof that always after a differential equation e prime is 0, so the rate of change of e is 0, then e itself is 0 all the time after that differential equation, if and only if e is 0 right now. No rate of change means it remains 0 all the time if and only if it is 0 right now. Together with the differential effect axiom that says that always after a differential equation a property p is true, if and only if always after the same differential equation the property p is true after we first assign f of x, the right-hand side, to the x prime variables, because that was precisely the effect that a differential equation has on the prime symbol. Notice that we follow a notational convention here. The differential invariant axiom and the differential invariant proof rule are very closely related by the differential effects axiom, and we use the convention that capital names are being used for axioms, whereas starting with lowercase names are used for the corresponding proof rules. The mnemonic is that axioms are the big ideas, so they've got big names, and proof rules are the ones that glue together all the little reasoning steps, so they've got little names. Or also, another mnemonic, axioms give you big trouble if you try to use them directly, because the proof rules that have little names give you little trouble because they already stapled reasoning together in exactly the right form. I personally find it more helpful to remember the axiom as the foundational principle, but use the proof rules in practice. The justification for these axioms for differential invariants is what we will carry forward to study even more axioms for other formulas of differential equations next time. They serve us very well in the future. The differential lemma relates once and for all a syntactic value with an analytic expression, the value of the differential of E with the time derivative of the value of E, at least along a differential equation. Otherwise, they might have completely different values because this side isn't even well defined if you're not in the middle of an ODE. The differential assignment lemma, which is captured beautifully in the differential effect axiom, which describes the effect that a differential equation has on the prime symbols. X prime is f of x. And the equations of differentials, which for the different syntactic forms that terms could have, since they're equations, tell us what their differentials are equal to. And the right-hand side is always simpler. Why? Well, because the value of the differential of E plus K is the same differentials but applied to simpler terms. So if we go from left to right, we make questions easier. The value of E times K, differential of that is a longer expression, but each of them has individual simpler terms, subterms as differentials. So E prime and K prime with some products of other things. The differential of the constant is 0. The differential of a variable is, well, the prime version of the variable, which is precisely what we will start out by justifying as correct next time, and using the differential lemma along with the others to justify the soundness of even more fascinating differential invariance principles.